going? Yeah. So today I want to give you more details about each of the two separate sides of the duality, and then in the next lecture bring these together. So first the ADS side, and first the theory in the bulk is the 2B string theory, which Waddy and Miriam both made use of yesterday. And I won't say any more about it than Waddy did. I'll say even less. I'll just remind you that the fields are the metric, the dilaton. There's a Neveu-Schwarz three-form flux, and there are Ramond one-form, three-form, and five-form fluxes. Actually, this is self-dual. And then there's odd dimensional D-branes. There's NS5 branes. There's bound states of these. There's probably more things I'm forgetting. But and all of these things, have some role to play in the duality. They all in various ways are reflected by physics in the gauge theory. We won't discuss all of that, especially the branes won't play a big role for us, but it's all there. So, and I could write down the Lagrangian, but you can find it in many places. I do want to do one calculation in this theory. So one thing I could do would be to write out the field equations and verify that AdS5 cross S5 is a solution, but that would be kind of boring. I want to do a reduced version of that, which I have found very useful for understanding scaling properties of a lot of these AdS solutions. So what I want to do is I want to dimensionally reduce from the 10-dimensional theory to a 5-dimensional effective Lagrangian, keeping only the fields that matter. And the fields that matter are just going to be the dilaton, the radius of the 5-sphere. So we'll think of that as I'll call it R, but we'll think of it as a field. That is the components of the metric G along the 5-sphere are proportional to R squared. And I guess also, of course, the branes, whether D or black, source this 5-form flux. And so there is on the 5-sphere, there's a 5-form flux. So we'll keep the 5-form flux. So the relevant terms in the action, and I'm going to leave out all of the constants in this part of the calculation. They can be put in. Miriam mentioned yesterday that I like to put constants in things correctly, and I waste a lot of time and sleep doing that. But for this calculation, we just want to get the scalings. And so the alpha prime to the 4th is the overall normalization, integral d10x root g r minus, and then f. Actually, I'm going to use capital. I probably won't be real consistent about this, but for 10-dimensional indices, I'll use capital letters. I should have used them over there, capital Roman, and then use mu and nu for directions along the CFT. So actually, these should all be Roman indices like these. Oops, and I forgot the dilaton. Well, here, let me. So the dilaton appears multiplying the curvature, but this is the string frame action. It doesn't, for reasons that are discussed in the textbooks, it doesn't appear in the Ramond flux action. And there's lots more terms. There's fluxes, other fluxes that aren't turned on. There are the gradients of these various things, but we won't. We're just looking for solutions where they're constant, so we won't need them. And so if we put in this ansatz, okay, first of all, the components of the flux parallel to the S5 are, we've got n units of flux, and otherwise dimensionally, I think it's out. Let's see, let me just check my notes on this. I think I wanted a -4 in front. Sorry, there's a -4 in the action, and dimensionally, this goes as alpha prime squared. And this comes from the Dirac quantization condition. That is the integral over the 5-sphere of this flux, regarded as a form, is quantized like the Dirac monopole quantization. The details, again, are, for example, in my book, and the quantization comes out like this. There's no factors of this r, this radius in the metric, in f, but they appear in this term because the indices get raised. So when we reduce to 5 dimensions, so d5x, then just the determinant of the 5-dimensional part of the metric, and then from the integral over the 5-sphere, we get its volume, which, leaving off constants, is r to the 5th. And then the curvature becomes the curvature of the 5-dimensional metric, plus from the curvature of the compact space, 1 over r squared, curvature of the S5 1 over r squared, and again multiplied by the dilaton. So these two terms both came out of here. And then the flux is minus n squared alpha prime to the 4th over r to the 10th. The r to the 10th comes from those 5 metrics that I raised with. Now there's a word here which, for the argument that I want to make, well, first of all, there's a subtlety with the 2B theory, which is that this 5-form flux is self-dual, and so you have to sort of, there's various ways to do, that complicates the action principle. One way to handle it, which isn't Lorentz covariant, but which is perfect for what I'm doing here, is to separate F into its magnetic components, which are purely spatial, and its electric components, where one of these is time, and then just treat the purely spatial components as the independent variables. And so I'm only keeping the spatial ones here. Choosing the spatial ones, that is the magnetic components rather than the electric energies, was nicer for this kind of thing, because with the electric energies, there's actually a surface term that confuses everybody for a while. And so it's always useful for the kind of argument I'm making here to work in a picture where the fluxes are spatial, magnetic. Even when you work with other fluxes, and I'm going to give you a homework problem in a few minutes, even when you work with other fluxes which are not purely self-dual, you have the option of 2 ways of representing them. For example, I called this a 3-form flux, but by Hodge duality, we could also think of it as a 7-form flux by contracting with the 10-dimensional epsilon tensor. And for this kind of argument here, you want to use whichever of these pictures makes the flux that you're looking at magnetic. Okay, so anyway, here's our reduced action. It's not really an effective action in the Wilsonian sense, because these modes, R and the others, are not lighter than all of the angular excitations of the 5-sphere. They're not a lot lighter, but because they're the only modes that preserve the symmetries of the problem, this reduced action will correctly generate solutions to the field equations. Okay, the next step is something which might upset Tom. I can never tell what's going to bother him. I didn't do this just for that purpose. It's just a bonus. But anyway, what I want to do is I want to interpret these terms as an effective potential. And in order to do that, we can't quite just, so this is the Lorentzian action. This is the Lorentzian action. So I might think that this is just negative to potential, but to really interpret it as a potential energy, we have to make a Weyl transformation to make the gravitational action canonical, just root GR, and then we can interpret the rest of the action as potential. So there's 5. The total number, if you take into account the inverse metric hiding in here and the metric here, we want to scale G5 to G5 prime times R to the minus 10/3 times e to the 4 phi over 3. If you do this scaling, then these rescalings will cancel off these things. You'll pick up derivatives that we're dropping. And so what you get is that this becomes alpha prime to the 4th integral d5x root g5 prime. And now just r5 prime. So again, the Einstein term is canonical. And now I've got to collect the factors of r from here and from here and from here and from scaling this G5. And instead of trying to do it in front of you, I'm going to copy it out of my notes. Plus e to the 4 phi over 3, r to the minus 16/3, minus alpha prime to the 4th, n squared. Okay, and so again, there's 2 fields here. There's two obvious massless, well, there's 2 SO6 invariant massless fields, the dilaton and the radius. And if you stare at this, you realize that actually this potential depends on only one combination of them. So this, I'm going to call this thing here, again, now I can interpret it as a potential energy. And that makes perfect sense in all situations. Sorry, that was just gratuitous. V of r and phi is minus 1 over x to the 4/3 plus alpha prime n squared over x to the 10/3, where x is the combination r squared r to the 4th e to the minus phi. So the potential actually only, there's a flat direction in the potential. The potential determines only this combination. In fact, okay, if you look at this, for large x, which means large radius and weak coupling, for large x, this is the dominant term. And then for small x, the flux. So for large x, so where do these terms come from? So the negative term originated from the positive curvature of the 5-sphere. Positive curvature in the compact space behaves like negative potential energy in lower dimensions. That's what you're seeing here, and vice versa. And the second term comes from the fluxes, and it's positive. When you try to squeeze the sphere small, the fluxes don't like that. When the sphere gets big, the negative term dominates, and so there's a minimum. The minimum is at x. You can quickly differentiate this and just see x is of order alpha prime squared. Thank you. Good. X is of order alpha prime squared n. And so r to the 4th is alpha prime squared n e to the phi. Okay, and so this is what was when I wrote down for you in the last lecture the black 3-brane metric and took its near horizon limit. This is in fact what we found for the radius of the 5-sphere with a 4 pi in there, which of course, we could of course actually have gotten if we had wanted to work harder with the current calculation. But so I've verified something that yesterday I just asserted, and also again you see that there's a flat direction. The dilaton, the string coupling, can take any value in the solution, and then the radius takes the comparable value. And again, we were using this yesterday. We were using our ability to vary this coupling between different limits to actually think about how this where this duality came from. Okay, so the homework problem, which is written out in more detail in the notes, is to extend this to three other cases, to M theory, which it's actually simpler than this because there is no dilaton, but to find the ADS4 cross S7 and ADS7 cross S4 solutions and their scalings of their radii of the radius of the sphere with the flux. And also, it's a little bit more work, but it works there too, the ADS3 cross S3 cross T4 solution in this same 2B theory. So these are M theory. This is all in 2B. So there's more details in the notes, but the homework problems are to just carry out this exercise for as many of these cases as you care to. Now, I like this because, for one thing, it employs the same highly sophisticated machinery of drawing potential energy curves that are used to discuss moduli stabilization. For instance, if we could find one more flux that we could turn on that was positive and that dominated at larger values of x, we could get a potential that looks like this or like this and has near de Sitter or that has de Sitter minima. In the present case, you can try everything. You can add anything you want. You can add more fluxes. You can add any of the branes, and you will fail this solution. And really pretty much, I think every solution for which we have an explicit ADS-CFT construction, basically because of the way the curvature is dominating at large radius, it turns out you can't find any term that pulls the potential up like that. This is a cartoon of what was done, for example, by Silverstein and by Koshru KKLT in stabilizing moduli, where the negative term in the potential came not from curvature, but from string instanton effects, which fall off in a very different way. Okay. Okay, we survived that part. So there's one more thing about these solutions, which is not so easily seen in 5 dimensions. It's more easily seen back in 10. And I won't go through the details, but it's important, so I'll tell you about it, which is that as I told you last time, and the radius of the ADS space, the curvature radius of the ADS space, is of the same order as the radius of the 5 sphere. And for the ADS5 cross S5 solution, this is exact. For the other cases, it's not always exact, but it always holds approximately. I should have said one more thing. Of course, what I've done here works in a precise way only when there's enough symmetry, as in these cases, that there's only a small number of possible modes of the metric. Even for less symmetric cases, where you really can't truncate to a small number of fields like this, even for less symmetric cases, this is often a useful way to figure out whether there can be an ADS solution and how it scales with the parameters. And maybe I'll use that later on. There's an example. Well, maybe I'll use that later on, or make it a homework problem. But in these cases, there's enough symmetry that it works. Okay, so the simplest way to think about this is that if you write out the Einstein's equations, there are, first of all, the Einstein's equations. They're the components parallel to the ADS space, and they're the components parallel to the sphere. And they each have 3 kinds of terms. They have the curvature of the ADS space plus the curvature of the sphere with different coefficients. plus various flux energies, matter energies, call it, and equals 0. They both take, so the Einstein equations, the two components again, this one and this one, both take this form, and as a result, all three terms in the equation are of approximately the same order. And that in particular means that the curvature radius of the ADS space and the sphere are the same. This is true, in fact, I think in all explicit examples of the ADS-CFT correspondence, this is true. The ADS space is approximately the same size as the positively curved pieces of the compact space. Sometimes you can make some of the coordinates in the compact directions smaller, but not all of them. So this is not, you can't really think of this as a compactification in the usual sense that the compact space is much smaller than the ADS part. But okay. Now it's interesting because in those KKLT constructions that I was mentioning, where you get ADS solutions and de Sitter solutions by some cartoon of this using other kinds of ingredients. In fact, it's claimed that there are many solutions where the size of the compact factor, which isn't a sphere, it's some kind of Calabi-Yau space or something with fluxes. But there are constructions from string moduli stabilization of ADS cross a small compact space, where the size of the compact space is much smaller than the ADS scale, and there should, by general principles, be conformal field theory duals of these things, but no one has yet figured out how to construct them directly. This was one of the challenges that Tom and collaborators set forward to the existence of the landscape, that there's all of these ADS solutions with no known CFT duals, and this is still an open question. Finding duals where the ADS is big and everything else is small. Okay, so any questions about this, what's about so far, this calculation, or any of the other connections? Okay, so a few more words about ADS. Actually, many more words about ADS. So, okay, so writing the metric in terms of the z coordinate, it's ds squared is L squared, dz squared plus eta mu nu dx mu dx nu over z squared, which is flat up to, it's conformally flat. And so you can immediately identify the light-like geodesics. They're just straight lines in this coordinate system, in particular focusing on radial geodesics. So this is the z direction, this is the t direction, and they just move at 45 degrees in the zt plane. So if we're sitting here at some finite position, a light ray can reach the boundary and return to you in finite, can reach z equals 0, can reach z equals 0 in finite time and return to you. This is a very special property of this space. It has gravity, but it has a boundary. Because of the warping, the metric actually doesn't fluctuate much as you approach the boundary, so it's a place where you can stand and make observations, but also it's a place where you have to impose boundary conditions in order to get sensible propagations. This is a boundary. On the other hand, the geodesics heading to or coming from positive z, since z runs out to infinity, take forever to reach there. They never get there. Yes?
In the previous part,
yes?
Does it make sense to use
To use, sorry?
Different file manifold instead of S file.
Yeah. So in fact, it's not any Einstein space, any space which is positively curved, whose curvature whose Ricci curvature is proportional to the metric, will satisfy the field equations. And there are many, many generalizations of this particular example based on that strategy, and I'll talk about a few of them. Yeah. So now this is called the horizon. And actually, it's kind of funny to call it the horizon. The horizon sort of implies that you can fall through it, which is sort of true and sort of not. That is, there's a sense in which these coordinates don't cover the whole space, and I'm about to describe for you what the whole space is. But in fact, if you're an applied ADS-CFT person and you're doing your experiments on flat four-dimensional space-time, really, this is the whole picture. Everything that you see is related to some calculation in this space and not some extension of it that a general relativist might tell you about. Actually, this idea that a geodesic takes forever to reach z equals infinity is very natural if you think about where I told you z comes from. So z was just the size of this gluon dipole, or more generally, it doesn't have to be a two-particle state. Actually, when you look at the whole dictionary, it could be a color singlet state of any number of constituents. But this theory is scale invariant and Lorentz invariant, and so these constituents move away from each other at the speed of light. And so when something is approaching z equals infinity over long times, it just means that in the conformal field theory, it's getting bigger and bigger and bigger. And this is also why for the applications, you can never fall through the horizon, because after all, you always turn off the experiment after a finite period of time. And so this spreading cloud can never become infinite in size. There's really always secretly some kind of infrared cutoff on large z, which usually will come from temperature or some other perturbation. So for many purposes, this is the whole space. But now I'm going to tell you the opposite. I'm going to tell you about the rest of the space. One more thing about this space again, which is another way to think about what the z coordinate is. So again, this tells us that if we have, say, a time interval, d tau, it's equal to L over z d x naught. Just the dictionary between the Poincare time coordinate and the time interval measured by some local inertial observer. Similarly, if we compare the energies, it would just be the inverse. The energy measured by some local inertial observer goes inversely, z over L times, I'll call it P naught, the energy conjugate to this, or turning it around, P naught is L over z times the energy seen by some local inertial observer in the space. Now, P naught is the conserved energy. P naught so the symmetry is translation of x naught. The conserved quantity is conjugate to that, it's P naught. And so the conserved energy is related to the energy seen by a local inertial observer in this way. And so in particular, if we have some observer with some clock or something, some definite scale, as that observer moves towards the boundary z equals 0, that's a much higher energy state in the CFT. As the observer moves towards the horizon, it's a lower energy state. So this is sort of complementary to this picture of the dipole size. It's in momentum space now, or energy space. And it's saying that, roughly speaking, where this fifth dimension comes from is that the energy scales the internal energies of excitations in the gauge theory are local in this new dimension. Okay. So even though this might be all we need for the applications, there's a reason to talk about the larger space that you can access if you sort of fall through the horizon. There's actually 4 reasons. The first is it gives us a picture of the space, even of the smaller space, that makes the symmetries more manifest. Second, we can use it to take advantage of the state operator mapping in conformal field theory, as I'll explain shortly. And third, if your real secret interest is to quantize gravity and not solve high TC, then it's better to think about physics in the larger space, the complete space, basically for the same reason that when you build a particle detector, you want it to cover 4 pi and not 2 pi of solid angle. You sort of want to capture everything. So this larger space that I'm going to tell you about is where you want to think about sort of doing controlled experiments on quantum gravity, but it also has some specific applications to the applications. Okay, so I want to start with this. What I want to do is I want to embed this space in. So we're talking about. Let me be general rather than talk about ADS5. I'll talk about ADS little d plus 1. So I'm always going to use little d for the number of dimensions in the CFT, and that plus 1 for the number of dimensions in the ADS space. And what we're going to do is we're going to actually write this as an embedded surface, a surface that looks like, an embedded surface in d plus 2 dimensions. And so the d plus 2 dimensions will have metric. And I think I settled on -1, 1, 1, 1. So first the d Poincare directions. This is x0, and then another 1 and another -1. So the first one is x0, and I guess the last one is xd plus 1. So this is, we'll call this, I'll call this gamma AB. I'll call the general coordinates here xa. The metric is L squared times gamma AB dxa dxb. And to get it down to ADSD plus 1, there's an embedding condition that gamma AB xa xb is -1. So I try to draw a picture of this. It's some kind of, hyperboloid of rotation in this space. But there's 2 time-like directions, so it's a little hard to draw. So this immediately makes something obvious. The symmetries of this space are SO d comma 2, because both the metric and the embedding condition respect that symmetry. I'm not sure. It depends on because it's time-like. It's time-like. So if this is a time-like direction, I think I want the base to it to be up here. There's 2. Well, I want to get. You're right. You're right. You're right. You're actually right. You're right. I'm going to use. I knew I wanted that because I need later to emphasize the fact that I need a blackboard with 2 time coordinates. Do we have one? Sorry. Okay. You're right. So let me draw it again. Well, I'll draw it better later and explain why I'm drawing it then. Thank you. Okay. And so there's not an obvious symmetry. I guess it would be useful to connect it to the form of the metric that we've been working with. So let me do that fairly quickly. We want to take these first four, the first d coordinates, and identify them with the Poincare directions. And then we want to take these last two directions and form null coordinates. So u is xd minus xd plus 1. V is xd plus xd plus 1. The metric is then ds squared is L squared eta mu nu dx mu dx nu plus du dv. The embedding condition is eta mu nu x mu x nu plus uv equals -1. And if you use these conditions to eliminate v, so we have one too many coordinates. If you eliminate v and you define little x mu to be big x mu over u and little z to be 1 over u, then indeed you'll find that this metric becomes the metric that we've been working with, which shows a number of things. It shows, again, that this is the symmetry. It shows that in fact, the metric can be extended from positive u, which is obviously all we were covering before, that the metric extends smoothly. It doubles smoothly because we can extend it from positive u to all values of u, positive and negative. And now coming back to the point that was just being made by the questions, the full space is really much bigger because if you look at the embedding equation, then you see that taking into account those negative signs, let's see, what I want to do is I want to move the 1 there. And you see that x0 squared plus xd plus 1 squared is greater or equal to -1. So there's like a hole in this plane. There's a non-contractible circle. If we draw it, so now I'm going to try to draw the picture that was requested before. It's this one, where this is a time-like direction, say x0. This is a time-like direction, xd plus 1. This now is one of the space-like directions. So it's not that I want to draw it, but it's okay. So again, there's a hole in the space. You can go. It's multiply connected, and so we can unwrap that space. And when we unwrap that space, we get the full global ADS. So the covering space, global ADS. Okay, and in particular. I won't write out the entire, it's in the notes. I won't write out the entire natural coordinate system to use for global ADS space. But the time coordinate, okay, so we can write x0 is the square root of 1 plus sum I equals 1 to d xi squared times cos t. Xd plus 1 is the square root of 1 plus sum I equals 1 to d xi squared sine t. And in the periodic space, is that right? Yeah, these satisfy these solve that constraint. And in the periodic space that we started with, t runs from 0 to 2 pi. Maybe I'll call it tau. tau runs from 0 to 2 pi. And in the covering space, the global ADS, tau runs from minus infinity to infinity. Yes?
So I think technically the symmetries actually don't act on the quantized hatch because they take you out.
They act infinitesimally on it. Thank you. They act infinitesimally, but not. They can't be exponentiated, right?
Somehow in the field theory, I think they can be exponentiated into the full global conformal, into the full conformal, even in R4.
Does anybody know that? Tom?
Yeah.
Yes.
So what happens is that conformal field theory can be formulated in Minkowski space,
Yeah.
or it can be formulated on the sphere across time.
Yeah.
Those two systems are not related by a unitary transformation.
Yeah.
They correspond to a singular conformal transformation, which is the stereographic projection of the sphere onto the plane, onto the infinite Euclidean space. And that in the sphere across time formulation, all of the conformal group acts as unitary operators.
Yeah.
In the
Right.
projected theory, which is not unitarily equivalent, only the
Yeah.
Poincare cross-dilatation symmetries act as unitary operators.
Oh, okay.
That's the special conformal transformation, which move the point at 0 or any point you like to infinity if you do them by a finite amount, because they're moving you on that sphere. Those transformations are not implemented unitarily in the theory on Minkowski space. And so the actual spectrum of the generators, all of those things are very different in the two different formulations of the theory. Despite the fact that there's not a unitary equivalence between the two, you can map the Green's functions computed in one into the Green's functions computed in another in a very well understood way. So one theory contains all the information you need to get the other one. And for those of you who are familiar with perturbative string theory, this is just the usual transformation from the cylinder formulation of conformal field theory in 2 dimensions to the formulation on the
But it's more complicated, right? Because the transformation is anomalous because there's
It's anomalous in
4 dimensions. Because
in worldsheet theory too. This is the Virasoro problem.
Yeah, there's the central.
sorry, in pure string theory, it's not anomalous.
Yeah, because C equals 0.
Yeah, that's right.
But that's because pure string theory is not a positive metric quantum field theory.
Yeah.
Because it has the ghosts of the X naught field.
Yeah, but somehow that's why you're allowed to do it in string theory, right? It's because somehow everything works out.
No, you're allowed to do it here too. You just have to take the anomaly into account when you transform them.
Okay.
So it's
Okay.
completely well understood how to go from one framework to the other, but it's not a unitary transformation.
Just to reiterate a few points from that discussion, if you were interested in the theory not in 3 flat dimensions, but in 3 dimensions of a sphere, remarkably, that would be dual to the times time. That would be dual to the gravitational theory in this space. And also, well, we'll use this again later, but in perturbative string theory, we have this state operator mapping where you kind of have an operator, you surround it, you go to radial quantization, regard that as time, and it gives you an isomorphism between local operators and states on a circle. In higher dimensional CFTs, you would surround a local operator with a d-1 sphere, and there's an isomorphism between the space of local operators and the states on the d-1 sphere. Okay. So just very briefly, how this SOD, 2 relates to the original Poincare symmetry. So here's how SOD, 2 acts, where epsilon is antisymmetric when you lower its indices. And so epsilon mu nu would be Poincare. Epsilon mu u would be Lorentz. would be translations. Epsilon UU would be scale, and epsilon mu V would be the special conformal transformations acting on the Poincare coordinates. So they're all in there in SOD, 2. Okay. So, good. So the next subject, and it's looking like it's probably all I'll get to today, is putting scalar fields in anti-de Sitter space. So, scalar field with standard action. I'm going to put an arbitrary normalization constant eta in here for later reference. Okay, so this is just the Klein-Gordon action written out in these coordinates. Z squared partial z phi plus z squared partial mu phi eta mu nu. So all these are minus m squared phi squared. Okay, let me think about what I want to say about this first. I think I mainly want to discuss, of course, its behavior solutions near z equals 0. Okay, no, I'm sorry, there's one thing I forgot. There are L's in the metric, and so what appears here is m squared L squared. Okay, now, good. So the first thing to discuss, in fact, is stability. What are the allowed values of the mass squared? And that becomes clearer if we work, instead of with the scalar field, we absorb some factors of z. We write phi is z to the d over 2 times psi. And also, I think it's a little bit easier to use a logarithmic coordinate. So z will be minus log y. So what minus y runs from minus infinity to infinity, where this is the boundary and this is the horizon. For y? Sorry, do I have it the wrong way around? Z is e to the y. Y is log z, sorry. Thank you. Y is minus log z. Z is the one that runs from 0 to infinity. Y is the one that runs from minus infinity to infinity. Right, good, good. Okay. And then the action becomes eta over 2, integral d dx dy. And let me look at my notes again. Partial y psi. Oh, I'm going to put the minus sign all in front. That's convenient. Partial y psi plus e to the minus 2y eta mu nu partial mu psi partial nu psi plus m squared plus d squared over 4 psi squared. And then there's a surface term from the change of variables when you collect things together, and the surface term is plus eta d over 4 integral d dx psi squared evaluated at y equals infinity minus y is minus infinity. Okay, so now the interesting thing is that this system, well, can be stable for negative values of the mass squared. Again, this is the action, so it's minus the Hamiltonian. And you see that, in fact, as long as m squared plus d squared over 4 is greater than or equal to 0, every term in the bulk part of the...
Joe, you dropped the L going between those two.
Thank you, thank you. Thank you. As long as this condition holds, allowing some range of negative values of m, all of the terms here are positive, except the surface term. Because, again, this is plus, but it's in the action, so it's minus. So if we add a surface term, if we add minus zeta eta integral d, so the negative one is the upper limit, the boundary term, which is where we can fix things, psi squared at y equals infinity. If we add a boundary term, then you see that for 1 over 2, for zeta greater than or equal to d over 2, the Hamiltonian is positive definite. Every term is positive, or semi-definite, I guess. Actually, you can be a little weaker than this, and this will be useful to us in some future lecture. In fact, it's sufficient that zeta be greater than or equal to something I'll call delta minus, which will soon be defined. This is a number slightly smaller, so each term is no longer positive, but you can show that the Hamiltonian can be collected into a sum of squares. Anyway, so but the bottom line is that in fact, and it's important for the applications, of course, that negative mass squareds, to a certain extent, are not scary here. The system is perfectly stable. That's because basically the boundary conditions force there to be gradient energy, which partly offsets the negative energy from the potential. If this is this is the Brighton-Loder-Friedman bound, and if this is violated, if the mass squared is less than this, more tachyonic, then the system is unstable, and you can't fix it with any kind of surface term. You can find very long wavelength excitations in the bulk where this is the dominant term and it's negative, and so the system is unstable. So interestingly, well, these are just the quadratic terms in the action. If you have positive quartic terms, there is the possibility of turning the potential back up and stabilizing things. And as you'll hear from probably more than one later lecturer, this violation of the BF bound leads to interesting phase transitions in various situations. But I won't talk about that. I'm going to always assume this. Okay. Okay. The field equation, I guess I will, I'll cover this up unless there are questions about it. The field equation in momentum space is and near the boundary, near z equals 0, the momentum doesn't matter. Things become ultra-local. They don't depend on the momentum. the behavior is the dominant behavior depends just on the mass squared. Phi k for any k goes as z to the delta, and if you plug this in, you find that this has to satisfy delta times delta minus d is m squared, L squared, thank you, or delta is d over 2, delta plus or minus is d over 2 plus or minus square root of d squared over 4 plus m squared. And again, this is real exactly when the BF bound is satisfied. And this is the delta minus that I used on the previous blackboard. So near the boundary, we have two modes in position space. Phi of x, z in x goes to alpha of x, z to the delta minus, plus beta of x, z to the delta plus. And let me leave aside the degenerate case where the two roots are equal. It would be natural. So now, because this boundary is at finite distance, we sort of have to apply one condition on these two coefficients in order to get well-defined propagation. And the natural one would be to set the larger coefficient to 0. Now, and with that, you can check that the action converges as at the boundary, and so everything looks good. Okay, now actually, so I'm not going to I'm not going to get into the dictionary today. Delta will turn out to be the dimension of an operator, and alpha and beta will have their interpretations. But the thing is, in the standard quantization, basically beta of x is being quantized. We have a box. ADS space is just a box. It's a very special box that can hold gravity. Gravitons reflect off the boundary. And there are quantized modes in it, states in it, and the quantized fields near the boundary have this beta behavior. For now, the larger thing is being fixed. It will be useful later on when we talk about observables in the theory to turn on fixed non-zero values. So in the standard quantization, alpha is fixed and beta is quantized. Now, to a limited extent, it's possible to make the opposite choice. That is, there's the alternate quantization where alpha of x is quantized, is allowed to fluctuate, and beta of x is set to 0. If you look at the action, it looks like it diverges with this choice. And there's one surface term that fixes everything. If you add that surface term that I actually had on the last blackboard, this one with zeta equals delta minus, then what you'll find is that, first of all, the energy is still bounded below. this was, I emphasized, on the last blackboard I emphasized that this was sufficient for the energy to be bounded below it. The system is stable. The action is actually convergent due to cancellation between the bulk and the boundary. And also, by the way, if you look at the surface terms in the equations of motion, they are non-zero separately, but they cancel between the surface term and a total derivative from the bulk. So the surface terms in the equations of motion vanish. Okay. Yes, question?
Are you drawing a distinction between finite energy and non-normalizable, which you say sometimes?
Here, so I haven't used the word normalizable or non-normalizable yet because I'm just saying that you have an action which is, and in Hamiltonian, which is finite on these modes. It's finite on these modes provided that it doesn't, you can't go arbitrarily far. The minimum value of delta minus is d over 2 minus 1. So let me not use the word normalizable for a second because I get confused by it, and maybe you can help me out. But just to draw a picture, of the possible values for the delta of the fixed, of the quantized mode. Here's d over 2. Here's d over 2 minus 1. And then it gets, more and more positive. It's infinity. You have all of these possibilities where these all come from what we're calling the standard quantization. And this little bit here comes from the alternate. But the reason we're doing, well, one reason we're doing this is to be complete, but the other reason is when you look at examples of ADS-CFT duality, although not the ADS-5, but more general examples, it turns out that you need to make use of all of these solutions. Actually, I can fill in a little bit more. When we get up to D here, D is the crossover between where the mass squared is. So over here, the mass squared is positive. Here is 0. And over here, the mass squared is negative. That's the D, dimension equal to D. Delta equal to D is the boundary between those. So actually, in the standard quantization, it's very clear that we also call this the normalizable mode. And we call this the non-normalizable mode. But I'm confused by what terms to use. Maybe you can help me out here. I'm confused simply by what words to use here because we're allowing the it's the bigger mode which is being allowed to fluctuate and the smaller mode which is being fixed.
In that little window, both
Yes.
modes are normalizable.
You want me to call them both? So that's for that reason I'm going to use the term fixed and quantized to avoid yeah, I'm going to call them fixed and quantized. And with this, and I would have been happier just doing this case in the lectures, and maybe I should have. So, but I'm going to use fixed for what would ordinarily be non-normalizable, and quantized for normalizable. And in the ambiguous case, I don't know what your convention is. Yeah.
I think you say they're both normalizable.
Well, they're both effectively they're both normalizable in that case.
You can do the standard quantization also.
Yeah, well,
That's right. That's right.
You do that. Well, there's a whole class of ones where you just got.
Indeed. These are not the only. Thank you. This is actually something which we'll come back to. It looks like it's getting back. It's getting pushed back to the 5th lecture, but in fact, there's an interesting story with this that. But these are the only conditions that are conformally invariant. There are more general conditions where there's some functional relation between alpha and beta, which are interesting, but they're not conformally invariant. And the breaking of conformal symmetry is something that we'll talk about later. But conformal symmetry leaves invariant either of these conditions, and so these are conformally invariant ways that they can correspond in some way to conformal field theories. Yes?
So does anything different happen for d equals to 2?
So you mean for D, for CFTs in 2. So 1 plus 1. So let's see, the most obvious thing that's happening here, of course, is that that's the case where, I said that normalizability required that you be on the positive, that it was an inequality, not that it didn't include that point. And unitarity implies that, in fact, if you have this is actually jumping over to the other side of duality, but this would be dual to a free field, not an interacting field. In 1 plus 1 dimensions, free scalars have dimension 0. So that's the most obvious thing that comes to mind. But I'm not aware, otherwise of any subtleties in duality for 1 plus 1.
The notion of normalizability and normalizable modes.
You still have the same two quantizations there. Yeah. I was afraid now you're going to ask me about how about 1 plus 0? How about ADS2? Because then this alternate quantization seems to push down to negative dimensions. Does anybody know if that works? Yeah, I don't know anything about that. Okay.
Well, in that case, don't you have to switch?
Well, I'm not. I shouldn't have put words in your mouth. Let's pretend you didn't ask that question. Yes. Okay. So really, this is all that. This is what I wanted to say about the one side of the duality. Tom said he's going to need this in his lecture today, some of these things. So since I have 5 or 10 minutes left, I'll just say a few minor things about the CFT side. Just generalities, things which are basically straight out of, the CFT on the string world sheet, but just asserting that they hold in D dimensions as well. So in a conformal field theory, the natural observables are correlators of local operators, and in particular, it's natural to work with operators that have a definite dimension. So under scale transformations, they transform to zeta to the delta, I want to get the sign right, O of zeta x. And I won't do it now. I'll do it early in the next lecture. In one line, we can relate this scaling in the CFT to things that we've just learned about the ADS side. In particular, this implies that the 2-point function and you can work it out just from that scale transformation, is just some number over the separation to the 2 delta. Any 3-point function can be reduced to a single number with its position dependence fully determined. So it's just a number. So in fact, the nice way to think about this is in terms of the operator product expansion. Times some function of x, which is determined by the symmetries. And if you want to, you can think about a conformal field theory abstractly just in terms of these coefficients and the dimensions. in particular, you can take an endpoint function. You can take an endpoint function and reduce it by successive use of the operator product expansion to a two-point function, just getting rid of operators one at a time. This expansion has a finite radius of convergence. It's a neat thing about conformal field theory. So you can actually use this to construct any endpoint function just out of the CIJKs. And if you have a four-point function, say, you can do this in two ways. And so there are associativity conditions on these operator product coefficients. And that is more or less all it takes to have a consistent theory. And in particular, what we'll say, well, it's not the operator product expansion really is just the insertion of a complete set of states in radial quantization. And these are a very loose set of axioms, and they're satisfied. As you see, any gravitational theory in de Sitter space allows us to define things that satisfy these automatically. There's always a special operator, the energy momentum tensor, whose dimension is d, and whose operator products are constrained by the fact that it's conserved and by the transformation properties of the other fields. Okay, actually, in my notes I wrote this a little bit more carefully. Sorry, this is something of order x to the delta k minus delta I minus delta j times O sub k. And pretty much everything that I've just written on the blackboard is, of course, just pulled from the string world sheet, and again, just being asserted to hold in arbitrary numbers of dimensions. Okay, so I think I'm going to stop here, and next time I'll say a few things about the n equals 4 theory, and then the dictionary. More questions?